Okay, this video is concerned with deriving the limit or the approximate distribution of the t-statistic. And there's going to be a second video that is discussing the distribution of the Wall statistic. Now, this video is designed to really go step by step in showing how to derive this approximate distribution of the t-statistic. I think it's more useful to consider such a derivation than the derivation of the distribution of the t-statistic in a finite sample context for OLS, where we need a lot of assumptions to figure out this exact distribution. Now, in modern day econometrics, the path taken is different. It's this limit or approximate distribution that we're concerned with. And the good thing is that what we do here actually does not only hold for OLS, for the OLS estimator, but it holds in principle for every consistent and asymptotically normally distributed estimator, like the OLS estimator under the assumptions that we figured out in the lecture. So a consistent estimator means that here's my estimate B, it converges in probability to the true parameter values beta. Now B generally is a k by 1 parameter vector of estimates. Approximate normality is obtained when we get the result that if we take the sampling error estimate minus true values scaled by the square root of the sample size squared of n, we get a convergence and distribution to a random variable x, and this random variable x is normally distributed with mean 0 and what we call an asymptotic variance covariance matrix B. So this A var of B actually is the variance covariance matrix of that random variable x. Okay. Now, this holds true for the joint distribution of the vector of parameter estimates B, but by the property of the multiple normal distribution, it also holds true for every element of the parameter vector B, right? For B sub k, for instance, as one parameter estimate out of the parameter vector B, okay, and we can also, the general result that the joint distribution is the normal also holds for the marginal distributions of every parameter. So I wrote this here. So sampling error with respect to case parameter estimate scaled by square root of n converges to a normal variable x. So this is a slightly smaller x here. And this random variable x is normally distributed with the mean 0. And this variance that we have here, we denote this as the asymptotic variance of B sub k, but it's really the variance of this x object that we have here. Okay, so that's the setup, and turns out that in many econometric applications, not only OLS but in other estimators that we shall consider in the lecture and that you will consider later on in your academic education, the estimator will have that property, consistent and approximately normally distributed. Okay, now for practical purpose, what we're going to do is we need to figure out an estimate of the asymptotic variance covariance matrix. This is usually something that depends on a lot of unknown objects. Down here we have the result for the asymptotic variance covariance matrix for the least squares estimator. We derived that in the lecture, and you see that this asymptotic variance covariance matrix depends on moments that we typically don't know, and it also depends on the epsilon, which is a function of the betas, which we don't know, so we need to estimate this asymptotic variance covariance matrix. And generally, I'm going to denote the estimate of the asymptotic variance covariance matrix with a big head over the A var, and I assume that we can deliver a consistent estimate of the asymptotic variance covariance matrix, right? That's the A var hat. Now, again, in the OLS context, maybe I want to take a look to a consistent estimate that can be delivered. It's written in this term, also discussed in the lecture. We replace epsilon by the regression residuals E, and it can be shown that this actually is a consistent estimator for the asymptotic variance covariance matrix of B. And such a consistent estimate can be supplied in various contexts. Okay. Now, for the purpose of this video, we assume that such a estimate can be obtained. Typically, what we're going to be interested in applied work is to write, to figure out an approximation of the variance-covariance matrix of the estimates, right? And the strategy is then always the same. We take this estimate of the asymptotic variance-covariance matrix divided by the sample size, and we obtain the variance-covariance matrix of our parameter estimates. Now, on the main diagonal of this k by k matrix, you basically find what you want, namely the variances of your parameter estimates. For instance, the asymptotic variance of estimate of bk is obtained by taking a look at the asymptotic variance-covariance matrix estimate and taking out the kth row, kth element, and therefore the variance estimate of bk, single parameter estimate, is obtained by dividing that object by n. Now, the object of core interest for applied work is very often the standard error of your estimate, right? We denote it by SE of bk, and that is obtained by taking the square root of your variance estimate, and you may choose to report the standard error or the t-statistic or the p-value that is associated with the t-statistic or the confidence intervals in your paper. And you see how we get there from a theoretical result down to something that is empirically usable. Okay. Now keep this in mind and make sure that you've understood all the steps and the intuition behind these formulas, because this is now what we're going to use. So the idea now is to derive the limiting or approximate distribution of the t-statistic. And you know that t-statistics are absolutely prominent, very important for applied work. People report them, people interpret them. So what we need to know is, we need to figure out that what the distribution of the t-statistic is under the assumption that delivered us this consistent and approximately normally distributed estimator. Now remember, the null hypothesis of the t-statistic, as we consider it here, is that the true parameter beta sub k is equal to a hypothesized value b over bar k. The alternative being that this is not true. Okay, and the way we test this hypothesis is by the means of the t-statistic. So I'm going to write the t-statistic in various ways. It's t sub k. So what we're going to do is we take the estimate, b sub k, we subtract the hypothesized value b over bar k, and we divide by the standard error of our estimate. Right. This is how we always construct t-statistics. And as I said many times, casually, the distribution of that statistic under the null hypothesis is going to be something that is close to the standard normal distribution. So we need to take a look at the quantiles of the standard normal to find the rejection and non-rejection areas of our test. Now we're going to be a bit more formal here. Now, using the results that we have above, I can also write the t-statistic like this. Numerator is unchanged. Recognizing that the standard error actually is the variance estimate of bk, and I'm going to take the square root of that variance estimate, right? But also know that the variance estimate comes from our estimate of the asymptotic variance, which we divide by n. So using that information, I can write the t-statistic in yet another way. So I'm taking this n from the denominator in the numerator, right? It comes out with the square root of n here. This is my new numerator, and the division is by the asymptotic variance of bk, more precisely, its estimate. Now we take the square root of that thing. So it's the same expression, exactly the same thing. Now we can note a couple of interesting things about this object. So I like to take it and copy it and investigate this t-statistic in this form a bit in detail. Now take a look at the numerator. Right? What happens with the numerator of that ratio? Well, with the result that we have up there, we know that this converges in distribution to a random variable x, and this random variable x is normally distributed with the mean 0 and a variance that is denoted by a var of bk. Right? This is the result that we had up there. Okay, maybe I scroll up and we see, okay, that is something that we have here in this line. Okay, here is the result that we have. But note the slight difference. In this yellow highlighted term, I have b sub k, that's a true parameter value, and down here I have b over bar k, and that is the hypothesized value, right? Important difference. So my claim that the numerator converges in distribution to a normal distribution is only true if my null hypothesis is true. Okay. If b sub k actually is equal to the hypothesized value, okay, i.e. if h naught is correct. Okay, so the distribution of the numerator is only in the normal with that mean and that variance if my null hypothesis actually is correct, but that's okay. I want to derive the distribution of the t-statistic under the null, that is, assuming that the null hypothesis is correct. Now let's take a look at the denominator of the term. Now I have the estimate of the asymptotic variance of bk, and from what we have up there, we have a convergence in probability to the asymptotic variance of bk. Now we assume that our estimate of the asymptotic variance covariance matrix is consistent, so the estimates the estimates of the asymptotic variance is also going to be consistent. It's a pointwise convergence that we take a look here. Okay, so that's an important insight. I have actually a ratio of which the numerator converges in the distribution and the denominator converges in probability. So I could write this our t-statistic in a slightly different form, not having a ratio but a product. So I'm going to write the t-statistic like this. Nothing has changed, of course, but what I want to do here is I want to make the t-statistic ready for an application of a theorem that already proved pretty useful, namely the Slitsky theorem, one of the lemmas that we had discussed earlier. So I could write this t-statistic in yet another form that essentially reads it's an, sort of a random sequence, an times xn. Now, an is then conceived to be 1 over the square root of the estimate of the asymptotic variance of bk, and xn is the square root of n times bk minus the hypothesized value. Okay. Now both are random sequences conceptually. The asymptotic variance estimate is a random sequence. It changes when the sample size increases, right? And xn also changes when my sample size increases. I get different estimates, I get a different sample size. So these are random sequences. Both an and xn are random sequences. And I have something that converges in probability. I have something that converges in distribution. And that is what we need for application of the Slutsky theorem. Now, what I'm going to tell you is, and I want to do it pretty detailed, I want to argue that where to does an converge to in probability. So I'm going to argue that an is going to converge in probability to a non-random object alpha. So an is going to converge to alpha, and xn is going to converge to x. I'll come back to this later. So what I argue is that an is going to converge in probability to alpha, and this alpha is in the present context the square root of the asymptotic variance of bk. Okay. Now, why is that so? Well, let me argue in detail why this is the case. So here's my argumentation why I can actually claim this convergence in probability. And I want to do it really in detail, step by step, leaving nothing out. I'm basically using, to establish this claim, I'm using a continuous mapping theorem argument, right? Because remember, if I have a random sequence Zn, I plug that in a continuous function A, what I have is a convergence probability to A evaluated at beta, assuming that Zn, the sequence Zn, converges in probability to beta. Okay, that's this continuous mapping theorem for you restated. Now here in the present context, what I have is the Zn sequence is the asymptotic variance estimate of bk. Okay. And A of Zn is then the taking of this sequence square rooting it and taking its inverse. It's the function that I'm interested here. Okay. Now, if I'm able to supply a consistent estimate of the asymptotic variance, what beta is in the present context would be the asymptotic variance of bk, the thing I want to estimate with a bar hat of bk. Okay, so what I have here is, okay, an is the an sequence that we've discussed up here, right? So that's the an sequence. In the present context, we have an being A of Zn. Okay, that's a random sequence an, and alpha, which is the term here. Right, this is the alpha. Alpha is here A evaluated at beta. Okay. So by a continuous mapping theorem argument, I established that an is actually converging to alpha. So here's a summary of what we've shown. Basically, we used the continuous mapping theorem argument to show that this an sequence converges in probability to alpha, and the green side tells you exactly what the terms are, and how it is shown that we actually have this convergence probability of the first term, an to alpha, and here we see what an actually is in the present case. Now it's an invocation of the continuous mapping theory. With respect to the xn sequence that we have here, we already dealt with that. We know that this converges in distribution to a random variable x, small x, and I'll tell you in a minute again what the distribution of x is. Now we're ready, right? An converges in probability to alpha, something that is non-random. Xn converges in distribution to x, which is a random variable. So we are ready for an application of the Slutsky theory. So Slutsky, remember, is applied when we have the present situation. So an converges in probability to alpha, xn converges in distribution to x, and what can follow then is that the product of the two sequences an times xn converges in distribution to the distribution of a times x. The question is what the distribution of a times x is, and in the present context we can figure that out relatively easily. Okay, excuse me, this is not an a, this is an alpha times x. Now let us consider what we have. So alpha times x, alpha, that is, as written before, 1 over the square root of the asymptotic variance of bk, and x, this is a random variable which has a distribution that is the normal, and the variance of x is what we refer to as the asymptotic variance of bk. Essentially, you can see this as the variance of x. Okay. Now, when you take a look at the variance of x, a var of bk, essentially this is nothing more but, well, 1 over alpha to the square, right? What we can do is then to say, okay, what is then the variance of alpha times x? Well, it is alpha to the square times the variance of x. So that would be, well, alpha to the square times 1 divided by alpha to the square, and that is, of course, 1. So in our context, alpha times x is going to converge in distribution to a standard normal, right? And this is the limit distribution of the t-statistic, right? So what we've shown with these steps is that a t-statistic in its original form converges in distribution to this alpha times x object, and its distribution is the standard normal. Okay, that's what we showed. In other words, what we could argue is that our t-statistic is approximately distributed standard normal. Right? The theoretical result is a limit result. The t-statistic approaches a normal distribution, a standard normal distribution. In a finite sample, we could argue that our t-statistic is approximately normally distributed. And that is actually what is used for applied work. You compute the standard error as discussed above, and compute our t-statistic and argue that the distribution under the null hypothesis is approximately standard normal, right? We should note this here. All this holds under the H naught that our hypothesis is true. Now what you do with that then is you're going to, for applied work, you're going to report your standard errors obtained in the fashion discussed above, or you're going to report your t-statistic, or you decide to compute p-values based on the approximate distribution of the t-statistic under the null, or, which is what I do often and prefer, actually compute confidence intervals, right? You have the parameter estimate, and then you subtract z alpha half times the standard error of bk. You get the lower bound of your confidence interval, and you take bk and you add z alpha half times the standard error of bk, and you get your upper bound of your confidence interval. Okay. Now what z alpha is, z alpha half is, it is the 1 minus alpha half quantile of the standard normal. Okay, remember that in the finite sample results we had to look up the quantiles of the t-distribution with a certain number of degrees of freedom. Not needed here with any sample size. You're going to take a look at the quantiles of the standard normal distribution. Okay, and this 1 minus alpha half quantile of the standard normal, that's approximately about 2 for alpha being 0.05, a significance level of 5%. Okay. When you do the confidence interval calculation, make sure that you've understood and correctly the meaning of the confidence interval. So again, please watch out when you interpret it. Please do it as we have discussed it a couple of times in this lecture and also in the earlier lecture. Okay, and that essentially concludes what I wanted to say about the limit distribution of the t-statistic, the approximate distribution of the t-statistic. Why we're regularly going to look up quantiles of the standard normal table and not at the quantile table of the t-distribution. Actually, it's based on this asymptotic or limit distribution reasoning that we've outlined here. Okay, so what I would suggest is definitely take care, make sure that you've understood every step, and make sure that you also have the derivations ready in case they're going to show up in the exam. Okay, thank you for watching the video. If you have comments and feedbacks of any kind, please let me know. Thank you.